we want to look at an aspect of the structure of matrix A. Now we know, like we assume at this point, that we know what the row space and null space of a matrix are and how to find them. Fairly straightforward. Okay, we're going to let A then be a real m by n matrix, and we define a transformation from Rn to Rm as transformation of V is the product of A with the vector V. We're going to let the Greek letter rho stand for the row space, sort of a pun, and the null space n of A. We've established that these are orthogonal, or at least we've worked out a number of examples, and we've found that these are always orthogonal. And from this, we conclude that, and from other things, we're not going to establish now from the rank and so forth of the matrix, Rn then turns out to be the direct sum of the row space rho and the null space A. And we also have the column space, which I didn't mention in the heading here, but that is the row space of A transpose, because the column space is the space spanned by the columns of the matrix, and the transpose is just what you get when you take the matrix A and switch its rows and columns. And when you do that, the row space of A then becomes the column space of A transpose, and the row space of A transpose is then easily seen to be the column space of A. So, with that background, I want to draw a picture, because that's the main thrust of what I want to say here. Okay, so we have then the row space. And we have the null space. Now, these spaces are orthogonal, which is why I've drawn them as rectangular. Okay, these are orthogonal. Now, we have vectors in the row space. Okay, so let's just say V is some vector in the row space. And let's say that we have two vectors in the null space. Okay. If I add this vector to this vector, well, the resulting vector is not in the row space. That is, unless the nullity is greater than 1. So let's just assume that the dimension of the null space is greater than, I said greater than 1, the dimension is at least 1. So the null space doesn't consist of just the zero vector. There's more than one vector in the null space. So, and let's just call this vector n1 and call this one n2. Two vectors in the null space. As a matter of fact, I really guess I don't like that notation, because n is too easily confused with a dimension. I'm going to call this u1 and u2. So this vector would be v plus u1, and then we could add v to u2 and get a completely different vector. Okay? So maybe that vector would be depicted down here. And there's no geometrical meaning to any of these lines. They don't even have to be straight lines. They just indicate that this and this add up to this. So here we would have a vector v plus u2. Now, all the vectors that we get by adding v to vectors of the null space form what we call an affine space. And we don't need to get into that. We haven't really talked about it, but it's not a subspace, but it's related to the subspace in that if we subtract V from every member of that space, we get a member of the null space. Again, we don't have to worry about that. It's an interesting thought, interesting idea to think about. Okay, well, okay, this is just for one vector V in U1. One vector V in the row space. Now there are a bunch of vectors in the row space, and of course there are infinitely many vectors in the null space, infinitely many vectors in the row space. So if we add all the vectors in the row space to all the vectors in the null space, we get our entire space, Rn. Furthermore, and I'll get colorful on you here, if we have any vector in Rn, okay, now I'm kind of out of letters. I maybe want to call this a V, but I can't because I've already used V, I've already used U. If I use W, that's not great. So I'm going to use X. Okay? Any vector X here is equal to an X row plus an Xn, where X row is in the row space, Xn is in the null space. So we're going to have an X row and an X sub n. And these two vectors are what we add to get our vector X. Furthermore, the sum of these vectors, each of these vectors is unique. There's a unique vector xp, just one vector xp, and one vector xn that add up to the vector x. So I'm going to say this is unique. I'm not going to specify all the aspects of unique, partly because I don't have space, but I'll say again, this is unique in that for any x here, there's just exactly one way to do this. Okay? Exactly one vector here and exactly one vector here that add up to this. Okay? So I'll say only one way for any x. Okay. So this tells us a lot about the structure of Rn relative to the matrix A.